Yeah. So some. Uh,
Yeah,
yeah.
you're asking the question why this is a null space of Rn.
Why is
So
it a
this is
subspace of Rn? Yeah.
subspace of Rn. So yeah, this is the all the column vectors where uh, uh, it is not spanned by the not what you call independent vectors from the column.
Um no. Okay. So to prove this is a subspace, what do you have to check? Uh, so I had written three properties here. So one is 0 should belongs to S. For any two vector belonging to S, U plus V should belongs to S, and AU should also belongs to S, right? So if you have a matrix which is from Rn to Rm, and null space of A I have defined as X which belongs to Rn such that Ax equals 0. Now you have to prove the null space of A is a subspace of Rn. How will you do it?
Hello, ma'am.
One
Uh,
zero should be there in this.
yes.
Then any linear combination of these vectors should not fall into uh, the column space.
No, see, first is 0 will always belongs to null space of A, right? Because if I take any vector x belonging to Rn, Ax will always be, I mean, 0 will always satisfy this equation, right? 0 will always be a solution for this, right?
Yes, yes.
0 will always be a solution. So 0 will belongs to null space of A. So here null space of A is nothing but your S, okay? I'll just write it as S. So the second property that it should follow is if I take any two vectors, so uv from null space of A, then what do I have to prove? I have to prove that u plus v belongs to the null space of A, right?
Yes.
So how do you prove u plus v belongs to null space of A? From here we'll prove. So u belongs to null space of A. So what does it mean? That AU should be 0 and V also belongs to null space of A. So AV should be 0. Okay. So from these two, I can write A times U plus V to be 0. So from here, can you see that U plus V also belongs to null space of A, right? So from here, you can see that U plus V belongs to the null space of A. Similarly, the third property, it also satisfies. So third property is what? If I take any scalar A and multiply it with B, sorry, if I have a scalar A and V is coming from the null space of A, then AV should also belongs to the null space of A. So use the same property. So V belongs to null space of A means what? Your AV should be 0, and I want to prove AV belongs to null space of A. So it means I want to prove A times AV equals 0. Now A is just a scalar, right? So I can write A times AV equals 0. And this is already 0. So um, this is 0. So this becomes 0. So from here I can say that uh, AV belongs to the null space of A. Right. Now, uh, okay.
Hello,
Given,
ma'am.
yeah.
You have written, ma'am, matrix M cross N and A
Hmm.
up, just a scroll up and up, car.
Huh.
A Rn to Rm. How can
Rn
we
to
write?
Rm.
Yeah, so how can
So it's a linear transformation, right? So what is happening is uh, I am taking a vector from Rn. So like okay, so let's say if I have a matrix A, I mean this is the function A, and I am giving a vector x, which is coming from Rn,
Okay.
is coming from Rn, and I'm getting what? I'm getting ax, which is in Rm.
This is not clear, ma'am. Can you say once again?
Uh, yeah. Okay. So what is happening here is you take any vector x, you take any vector x, and a is your function. Okay, a is your function, and you are taking uh, so this ax equal b, right? And this function, when you take x, it's giving you ax, and this is an Rm.
But ma'am, what is the
Oh,
relation here, row and column for that function, this function? Matrix we have taken M cross N.
matrix we have taken m cross n.
M cross N. So why we are taking Rn to Rm? Why not we are taking Rm to Rn here in function?
Okay, let's see this, maybe let's see example. So you have a m cross n. Okay, so how does it look like? It looks like
M row
a11, a12, a1,
M
and it goes up to a
A1 M.
m1, a m2, a mn. And okay, I'm writing the system of equation to be, okay, I'm just writing ax. Okay, so this is what, this is x1, x2 up to xn,
Oh,
right? So now now you can write this as a11 x1 plus up to e1 and xn, and you will have am1 x1 plus up to amn xn. Okay, so this is more like I have, I can write this as, let's say, c1. I think even this is not needed. So okay, you can see here, right? So this is m cross n matrix, and this is n cross 1 matrix,
yeah.
right? So this is taking a vector in Rn, right?
Oh,
You are taking a vector in Rn, and when it gives you ax, this is an Rm,
okay.
sorry, this is an Rm.
Okay.
Yeah. Okay. Okay. So so given a matrix, how do you find the null space? So you have a to b, for example, let's say a to b 1 minus 3 minus 2, 4, 1 minus 3, 1, 1, 0, 0, 1 minus 1. So if you have a matrix given to you, how do you find the null space?
First, we have to find
We will
pivot
take the
in
row
the
echelon form.
row echelon form. Pivot.
We'll convert it to row echelon form, right?
Yeah.
So yeah, let me do it here only. The question is find the null space of 1 minus 3 minus 2 4 1 minus 3 1 1 0 0 1 minus 1. So can you do it? Yeah.
R2 minus R1.
R2 minus R1 will do. Okay. So yeah, we
Ma'am,
will.
they are not equating it to 0 ax equals b.
We are not equating it to 0 ax equal b. Um, no, we are finding the null space of this matrix, right? So null space is just you have to solve for ax equals 0, right?
Yes, yes.
So to find the null space, you have to do ax equal 0. So you'll get
Ma'am,
3.
one general question, ma'am.
Yes.
If we are given one matrix, so the
Okay.
maximum dimension we can have for the matrix is number of the columns, right?
Maximum dimension we can have
The number of column determines the
number of
dimension.
columns of A.
Yeah, that determines the dimensions, right?
That determine the
Number of null space.
dimension of
The whole matrix.
Also null space.
dimension of the matrix will be m cross n, right? So you're talking about the dimension of row space or dimension of column space. When the rank,
No, the entire the equations it spans in what is the
hmm,
maximum dimension in any space it can have is the number of columns, right?
Yes, yes, it's the number of columns.
yeah. So using rank nullity theorem, what we will have? You will have rank of A plus nullity of A. It should be equal to number of columns of A, right? So that is the dimension of, yeah.
Okay, the number
So
of the yeah.
in this case it is n. But if your matrix was a n cross m, then it will be m, no? I mean, when you write the rank nullity theorem.
No, my question is that okay, the in
Hmm.
terms of in any four fundamental space, the
Hmm.
maximum dimension we can have is the number of columns in the original matrix. Is that correct?
Yes,
Okay,
yes, the
the
number
rows,
of columns.
yeah, the rows don't have any importance in that. Even the rows are more than the columns. Still, column determines the maximum dimension, right?
No, the rank will be minimum of the number of rows and number of
Rank
columns.
is minimum of, uh, yeah,
How how can RAM will be the minimum? Because when we have a row, that means it's a variable. We are adding a variable, right?
when you have,
When you are having a column, every column that means a additional variable.
wait, um,
Because if we say x1, x2,
wait, wait.
x3,
Hmm.
It's minimum because rank of row and rank of column is equal. That's why it is minimum of rank and column.
Yeah, rank okay, we can say, but that space is still a higher dimension, right? Okay, now one example I can give you. If we have
Hmm.
okay, maybe three columns and
Okay.
five rows. Okay, there's only
Okay.
three variables. So that means there will be definitely some linear combinations of the row in the equation. Some of them definitely will go into what do you call it's a linear combination. We can have only maximum three.
Maximum rank would be
That
3.
maximum rank, yeah, rank will be 3.
Okay, then
Yeah.
yeah, suppose we have only maybe in this three dimension, all the we have only one pivot point. That means two either columns or rows are dependent, even though
O-
still this
Okay.
one this yeah, okay, yeah.
So let's say I have okay, this is also okay, maybe this. So let's take A to B, 1, 2, 3, 4, 5, 6. Okay. So what is the rank of A here? What is the rank
two
of A here?
Two, madam.
two two
Rank is 2, right?
Even if we add any number of rows, rank will be maximum two, right?
Rank
Yes.
rank will be maximum 2 in this case.
So
Yes.
that means but that means the column determines the maximum dimension.
Minimum of
Uh,
row and
Yes, yes, you are
dimension.
saying column determines the maximum dimension of the whole space. Yes, you are right
Yes,
there.
yes, yes, yes.
Column.
It is minimum of row, number of rows and number of columns.
Yeah.
It is rank, that is
Dimension.
rank.
because
But
it
the
The whole space.
dimension of the whole space is determined by the number of columns. Maximum number of columns, yeah.
Okay,
Yes,
here
madam.
even if we here even the if we do row, and if the other two rows are linear combination of the first row, so we are saying that it's only one. But even if it is one dimension line, it is still in a two dimensional space, right? Because the number of columns, the dimension of the entire space is two.
uh
Yes. Rank is
oh,
1 and 1 is nullity. So, yeah, the dimension of the whole space is 2.
3 rows and 5 columns. I see. Yes. Okay.
Even madam.
Max.
Yeah. Suppose we have matrix M cross N. So null
Yeah.
space belongs to R to the power N. So your column decide the dimension of null space. Yeah.
Yeah, when we add a column, that means we are adding a one more feature, what do you call variable, right? If we say x1, x2, x3, then one more variable we are adding. But when we are adding a row, we are not adding any variable. We are adding one more equation.
Null space belongs to R to the power N. It means, madam, a null space is a subspace
Mhm.
of R to the power N, or its dimension is equal to R to the power N. What did you have written first?
Just give me a minute. I'll be back in a minute. Okay. Yeah. Hello.
Yes, ma'am.
Yeah.
Yes.
You can tell now. What were you saying?
No, we are just understanding the space, okay, whether the adding rows will not have an impact in the overall space, but adding a column will increase the space, because columns are features, okay, and rows are not a feature. Rows are giving more information about the features. Maybe we will discuss later
Uh-huh.
this, ma'am. Ma'am, you can continue with the planned session, ma'am.
Yeah, yeah. Just hold on. Mm, okay. You can also okay. You can also write it in the chat box if you have any doubt in between. Okay.
Sure, ma'am. Sure.
Yes.
Okay. So how will you write the null space for this matrix?
So X2 and X4 are free variables.
X2 and X4 are free variables. Okay.
So first we take X2 around 0, X4 is equal to 1, then X4 0, X2 1, and simultaneously we take them. So first we have to solve linear equation X1, X2, X.
Yeah, so first we have to convert this to the echelon form, right? So it is still not in the echelon form, and
Okay.
this will be 1 and this will be minus 1. So I'll just write it here, and then you can just add to these two rows. So this will give you 0 0.
Yeah.
So the maximum number of so this matrix is uh, 3 cross 4 matrix, right?
Yeah.
And the maximum pivots it can have is 3, right?
Two, but
Amen.
No, no, sorry, in general I was talking. So okay, so here you see that you have 2 pivots, right? And these pivot columns, uh, these um, these columns where we have the pivots, we call it as a pivot columns, right? So now what you will do is you will write each of these. We want the solution for ax equals 0, right? So now just write it in as x1, x2, x3, x4. So you will get x1 minus 3x2 minus 2x3 plus 4x4 equals 0. Then you have x3 minus x4 equals 0. So x1 and x3 are basic variable, right? So you have x1 um, minus 2x3. This you can write it as 3x2 minus 4x4, and you get x3 to be x4. So what we do is we try to write the free variables, sorry, the basic variable in the form of free variables. So our basic variables are x1 and x3. So I have written x1 x3 as a function, as a function of free variable. So now from here you get x3 to be equal to x4, and from here I can write x1 to be um, 3x2 minus 4x4 plus 2x3, which will be plus 2x4, right? So this is just 3x2 minus 2x4. So the null space of A will just be all x. So x1, x2, x3, x4. And this is what? This is 3x2 minus 2x4. Um, then you have x2, then you have x4 and x4, right? So again, we can write it as x2 times 3 1 0 0 plus x4 times minus 2 0 1 1, right? So what is the null space here? It is just span of 3 1 0 0 and minus 2 0 and 1.
Yeah, madam, dimension of null space is 2. Nullity is 2.
Nullity is 2 here, yes.
Oh. And the dimension of uh, each base vector is 4. I think equal to column of given matrix.
Okay, so here we got, so see, number of pivots becomes the rank of, like once you convert the matrix to the echelon form, the
Yeah.
number of pivots give you the rank, right?
Rank. Okay.
So in this case, what is the rank of the matrix?
2.
It is 2.
Uh,
And the nullity of A,
is 2.
you have two free variables, so that is also 2.
Total number of columns is 2 plus 2.
Yeah, number of columns is 4. Yeah.
Ma'am, my question is why does the rank correspond to the pivot elements? Like, what is the connection?
Why does the rank correspond to the...
Because it is independent. An independent vector can span all space.
Because column 1 and column 3 are independent.
Yeah.
Yeah,
Because of that
because of the...
zero.
Huh. So when you convert it to the echelon form, right? After converting it to echelon form, so let's say if a matrix A, and you convert it to U, so the number of pivot, the number of if I'm talking with the column with respect to column, so the number of the columns which are pivot columns, they become they are independent. So pivot columns will be independent, and even and what happens is also the non-zero rows, they also are independent. So non-zero rows, non-zero rows of U, they are also independent. And uh, also, like, if you convert the matrix to the uh, if you convert the matrix to the row reduce to the echelon form, uh, so it doesn't change the row space of the matrix. So whatever the row space of A will be, the rows so whatever the row space of U will be, the same will be the row space of A also. And that just gives the and that gives the independent rows for the matrix.
So, madam, here again I have a question.
uh,
Suppose we have taken a matrix 3 cross 4. So, null space belongs to R to the power 4, but here the dimension of null space is 2 only.
Sorry, the matrix, your
We
matrix
have
belongs to where?
3 cross 4,
Okay, the same matrix. Okay.
3 cross 4. So, the null space belongs to R to the power 4. According to definition you have written previously, suppose we
No,
have
no, it is a
person.
subspace of R4.
Okay, that's why I am saying it is a subspace of R. Okay, okay, madam.
Ma'am, this everything theoretically it seems fine. I mean, to calculate or whatever nullity on the rank or whatever the case may be. But when it comes to real life applications, that time how will we connect that? That is the main question actually. For calculation purpose, I mean that is okay. That is the one thing. But
Yeah.
so that was my main concern actually.
Okay, so one application you will find very soon in the SPD. So there you will deal with the matrices of rank 1. So maybe when we go there, it will be easier to understand. So one thing, wait.
Ma'am, I have a doubt.
Yeah, Priyanka.
Ma'am, when we write this null space as a span of the vectors, like
Hmm.
when we found out in the above question that you just solved, so is it same if I write it as it was the vector column 1 and the column 3? So is it same if I write the original matrix from the question or after the reduced echelon form what I got, is it same? Can I say both are same? I can also say that the span of this, oh sorry, null space of A would be span of the vector from the original matrix. Is it same? This one, the one.
Um, you are saying if we can write null space of A to be
Fourth.
the first and the fourth
Fourth
column.
column from the question that we from this matrix. Yes.
See, that will be
No, we cannot
those
write.
will, yeah, we cannot write that will be the column space of A. If if you go, so uh, the pivot column, right? The pivot columns will give you the column space. I mean the original columns. Let's say the first column. So the first and the third column from U. So the first and the third column of U, sorry, the first and the third column of A will give you the column space of A and not the null space of A.
So first and third column of U will not give column space.
Sorry, the first and
Third
the
columns of
first and
A
third.
will span the column space, but what about
Yeah.
the first and third column of U, then row echelon form? This one.
So it will be right
Okay, wait.
motion.
Wait. Okay. This is not what we got right. Okay. Prashant, can you repeat your question?
The first and third column of A will span the column space.
The first and third column of A will span the column space, right?
What about
And
first and third column of row echelon form?
that will also span the column space. That will also give the column space of A.
So
Okay,
That
it
will
is
same
also.
same.
column space.
It is same as saying
But
if I
but
want
we
to
were
say
talking
that.
about null space, right?
Yes, I was confused because I thought it would be the same, but it is different. So now I am clear. So the column space and the original matrix spanning is same, but for the null space it will be different. It will be only the vectors that we found out. That will be the spanning vectors.
Yeah, basically the free variables that you get, they form the null space,
Okay. And also
not the basic one.
one more uh, I mean, how do we find? So there was this question in which it was asked that how can we span the entire 4D space using a four-column vector given by a 4 cross 4 matrix? How do I check that if a
Um,
particular,
okay.
yeah,
What is the question?
I'm just posting it in the chat. So I
Okay.
just want to know how to approach it.
Yeah, so your E1, E2, E3, E4 will span the entire 4D space, right? E1 is 1 0 0 0, E2 is 0 1 0 0.
Oh, okay. So if I will get the four pivot in that matrix by reducing it,
Then
yeah,
it will
then it means
span.
it can
Yeah.
span.
So
Oh,
one
okay.
example is your this identity I4, I4 cross 4.
I4. All right. Got it. Thank you very much.
Yeah.
So span and basis are both different, na ma'am?
Span and basis are yeah, they are different. So span, when we say a set of vectors, let's say v1 v2 up to vk, uh, if we say span of this vector, okay, and these let's say these vectors belong to a vector space v. So if I say span of these vector, it means we are just talking about the linear combination of this vector. But basis, what happens is basis, it should satisfy two properties. The first thing is that all these vectors, so span of v1 v2 up to vk, so should be whole v. So they this spanning should uh, they should span the whole space, and additionally they should also be independent. So why independent? So they should be independent. So why we need why independent is because if it is satisfies these two properties, then if I take any vector from this vector space v, so if I take let's say any x belonging to v, then I will be able to write uh, these vector uniquely. So basis should satisfy these two properties. I mean basis is basically this one. Like they should span the whole space, the whole vector space, and they should also be independent. And independence, so that you can write, if you take any vector from the vector space, you should be able to write it uniquely.
Okay, ma'am.
So like how uniquely is, like let's say I'm taking two vectors. Um, uh, okay, let's say I'm taking one vector x from V, and since the from the first property we say it sh- you should be able to write x as some linear combination of, so let's say I'm writing a1 v1 plus up to ak vk. Okay, and if I take another linear combination, so you will have, let's say, b1 v1 plus up to bk vk. Now if you take the difference, so you will get what? You will get a1 v1, you'll get, I'll just write it here, ei vi, they should be 0. And since these vectors are independent, because of the independence, this ai minus bi should be 0, and that means ai equal bi. So any vector, if you have the basis, okay, if you have a basis vector for a vector space, then if I give you any vector in from that vector space, you will be able to write um, the linear combination uniquely. That is what it means. Yes, okay. Okay, so if you have, let's say, an m cross n matrix, and your m is less than n, okay, so for any m cross n matrix, when n is greater than m, then in that case you will always have some non-zero vector such that your ax will be 0. So the example for this you already saw in the previous one. So whenever you have um,
Ma'am, this should be when m is greater than n.
this is when n is greater than m. N is greater than m, right? This is the matrix is m cross n. Okay.
Yes, ma'am.
Yeah. So why is this happening? So let's say I have a matrix A, okay, and it is m cross n. So let's say I am writing, um, so this is my first vector, second vector is xn. So let's say I have the linear combination. So if I take a linear combination of this, so c1 x1 plus up to cn x xn will be 0. Okay? So ax equals 0, what I've taken. Now this, you can also write it as the matrix A times c1 c2 up to cn, and this is 0. Okay, in this case, what will happen to the column? Will they be independent or dependent?
C's are zero, not zero.
C's are not 0, right?
Then dependent.
Then it becomes dependent. What happens if you have an n cross n matrix which is invertible? You have an n cross n invertible matrix. What is the column? Um, which one? Okay. So if you have the vectors given to you, let's say v1, v2 up to vk, how do you check for independence? Huh. How do you check independence? So I have given a list of vectors. I've given a list of vector v1 to vk, How do you check its independence?
Put the vectors in the column and find the pivots.
Or even through the determinant.
Even through the determinant, yeah. And like you have also studied this, right? If to check whether a set of vector is independent, you can also check for sum over ci vi, or uh, vi where I varying from 1 to k 0, and in this case all the ci should be 0. All the ci should be 0. So basically you should be able to write 0 uniquely. And what is this? So it is just 0 time v1 plus 0 time v2 plus up to 0 time vk equals 0. I mean, this is a unique way of writing 0. And whenever and whenever you have at least one c, at least one c, which is non-zero, then that implies these vectors v1 to vk will be dependent, right? So for example, let's take x1 to be 1 to 5, x2 to be 1 0 0, x3 to be minus 2 1 3, and x4 to be 1 1 1. Can you check if these vectors are linearly independent?
No, they will not be linearly independent.
Answer is no.
Yeah,
Yeah, why is that?
because here the number of unknowns are less than the number of rows, columns.
Sorry, I couldn't hear you.
Yeah, number of unknowns are,
Number of rows.
yeah, number of unknowns are less than the number of columns.
Yeah, here m is sorry. Um, Here n is greater than m,
Yeah,
right? So it means you will have at least one non-zero vector. Um, I mean, you have at least one. You will have at least one free variable, right? So it will not be full rank, and from there also you can say it is linearly independent. But did you check using this definition?
Yes,
no,
x1 plus x2 plus x3 minus 2 x4 is equal to 0. That's why it is not linear. Linear combination. One
Yeah.
coefficient.
So Yeah, this is one way to check using matrices, but you can also just check if you are able to write the zero uniquely or not. If you are able to write zero uniquely, then linearly independent. Otherwise, they are not linearly independent. That is also one way to check. Um,
But I mean, first method, how can you repeat once again? M is less than N. Then what means row less than column?
Sorry,
First method you have checked M is less than N.
M
Can you repeat?
is less than M. Yeah.
First you have to check M is less than N. That's why it is.
This is what I've written, right?
Yeah, yeah. And one of the
So this you can see from this example also, like the example which we did. So
yeah, yeah,
whenever your number of columns are more than number of uh, rows,
yeah.
so there will always exist some x, some vector, some non-zero vector, such that ax equals 0.
Uh,
In that case, in that makes yes, they can be at most at max 3 independent column.
So, ma'am, if any of the rows is not a multiple of the other row, so then in all the columns, then can we say that they are linearly independent
Uh,
just by checking multiples, or if like that?
yes, yes, you can check. So, yeah, you can check that way also. Okay. What is the rank of this matrix? You can find rank for this matrix by them. Yeah. So what is the rank you got for this matrix? Um, 3. Okay. Okay. Yeah. 3 is the right answer. Rank is 3. So, okay. The question is, does the system of equation, if I try to solve Ax equal b for this matrix, this does the system, does Ax equal b have a unique solution, or infinitely many solution? What would be the answer for this?
Infinitely many cells.
Oh, sorry,
Infinitely many cells.
infinitely many solution, right?
Because,
Because you have a one free variable in
yeah,
the
yeah.
matrix. So this will be the answer. So I remember last time we were asking for textbooks from where you can practice the questions. So Sham series have a on the linear algebra book. It has a lot of worked out examples that you can refer to. So you'll find plenty of questions, solved problems over here. Then another is linear algebra pure and applied by Edgar G. Kutai. This is also quite good. So there also you will find uh, like you will here also you'll find problems, nice problems. Okay, and then you have Hoffman and Kuhn. So this has slightly less problems, but it's a very good book. But if any one of you wants to refer, I would say it's a very good book for reference of Hoffman and Kuhn. And again you have Gilbert's trunk. So for this course we have recommended Gilbert's trunk book, right? So just look at all these four textbook and see which one is more better for you, and those books stick to any one book, or if you can refer to multiple it's good. But you'll
Okay.
find, yeah.
Madam, invertible and invertible matrix. Uh, what's the relation between invertible and independent matrix?
What's the relation between
Invertible matrix and vector.
invertible matrix and
Independent vector matrix. If matrix is invertible,
hmm.
so suppose a matrix, a square matrix is invertible, all vectors belong to that matrix are independent. Well,
Okay, okay. So if you have, let's say, okay, let's say this is an invertible matrix, okay, and you have to solve for Ax equal B, right?
yeah.
So now A is invertible, so you can also do A inverse Ax equal A inverse B. Now from here, to get a unique solution,
So how can you check
we will get a unique solution.
unique solution?
Yeah.
So unique
So unique
solution.
solution, you'll get unique solution. You will have full rank, and the null space will just only contain the zero vector.
So this is independent.
Uh,
Ma'am,
who's there? Oh yeah, Prashant.
if the matrix is invertible, then the columns are independent.
Columns are independent.
Then
Yes.
what about rows?
Columns are independent. What about rows? Um,
No, if it is invertible.
um, the rows will also be independent in that case. It will also be independent. Um, how do you prove it? See, column space will be rank will be n, and rank column rank is equal to row rank equal n, right? In that case, and if the column rank is n, then row rank will also be n, and row rank is also the linearly independent rows of A, so that will also be n, right? So using this, you can conclude that uh, even the rows will be independent.
Yes, ma'am.
Yeah. So both the column and the rows will be independent. When will the system does not have a solution? So you have Ax equal B, right? So when does the system or when does Ax equal B has no solution? So how do you check if the system of linear equation has no solution?
The determinant of A is equal to 0.
Determinant.
Okay. Determinant of B is equal
Determinant
to
is zero.
0.
Determinant is
Then,
zero.
yeah.
Hmm. Okay. And anything else you can tell? Uh, yeah, I
B
would
is
say
not
that
in the
case.
column space.
Yeah. The other thing is, yeah, you can say B when B is not in the column space. So determinant equals zero. Second, B does not belong to the column space of A. So yeah,
How can we check whether B does not belong to column space? That I know we have to check.
how do you check B does not belong to the column space? So how do you check B belongs to the column space? When how do you check this Ax equal to B have a solution? So to check the system has a solution, you check that B belongs to the column space of A, right? And to check this, you again uh, like perform the row reduce echelon form.
Yes.
So in the row reduce echelon form,
Okay.
sorry,
So all last row element of last row all element of last row is equal to 0, then
uh-huh.
it has solution. Otherwise, uh,
Yes. So all the elements of yeah. So the last row basically should be. It shouldn't be like all this last row is coming out to be zero, and you have
argument.
uh,
Yeah,
some arbitrary number over here. Then this doesn't make sense.
makes sense.
Yeah. So whenever a situation like this happens, in that case, you can say the system does not have a solution.
And does not B does not belong to column space.
Yes.
Yes.
How do you find the row space? Let's say I've given you
Column, column
one
space of A transpose.
column space of A transpose. But can you do it without uh, going for column space of A transpose?
Yes, by converting reduce row with echelon form and
Yeah.
with
So
non-zero rows addresses and a swarm of that message will
yeah, uh, you can just find the row space of U, and that will also be the row space of A. So you don't actually have to go to A transpose and then find the column space of A transpose. So you can actually go and do the row space. Go and convert it to echelon form, and uh, that will give you the row space for the matrix A. The non-zero rows of U will give you the row space of A.
row is
But the result from both the methods will be the same or we
So,
different the spanning set?
sorry.
The spanning set obtained by these two methods will it be the same or it will be different? Like finding the column space of A transpose and doing the
Ah,
reduced rows form.
it will be same. It will be same.
Because one of the practice assignments I got it different.
Okay. Can you tell me the question number?
Can you give me a second? I just
Yeah, sure.
practice assignment 3 question number
Question number
9.
question number 9. Question number 9. Can you tell me what is the question? Is it about finding the rank?
And
It's the
even
row
in terms of
space.
building apps that are mobile or that are on cloud or that are on prem, and that's where the products which
Ma'am, I joined a bit late. Is there some YouTube link available for the same?
No, YouTube link is not available, but update this.
The recording will be.
Yeah. Okay. The matrix there is 2468. The same one, right? 24681305
Yes, ma'am.
and as a result, Robert and I
1163.
keep working
Yes, ma'am.
very closely with each other in terms.
Okay. So when you convert it to row reduce echelon form, what do you get? Uh, can you tell me the matrix? Is
How we can transform clients by
Two four
by
six
having
eight.
ServiceNow as an ecosystem or a platform is something that we focus on. Josh and his team are experts in that space as well. While we call ourselves as a services organization, one of the biggest unique selling
24681305. 24681305. Um,
1163.
just give a problem as a bad day.
1163. Okay. What is U that you got? Okay, so let's do this. So I can interchange the first and the second row, and I will get 1 3 0 5 2 4 6 8 1 1 6 3. Then I will do R2 is replaced by R2 minus 2R1 is replaced by R3 minus R1. Okay. So we have 1 3 0 5 2 minus 4 minus 6 is minus 2 6 8 minus 10 is minus 2. Okay, so this would be 1 minus 3 1. This will become 0 0 0. Yeah, so the row space of A would be this row and this row, the span of these two rows.
The answer is different.
Sorry,
The answer is different.
the answer is different. It is not span of 1 3 0 5 and 0 1 minus 3 1. Have I done the correct?
But from in column space, we took original column of matrix, but here we have taken uh, reduce row of that matrix, a spanning of reduce row of that. That's the difference. Hello.
Ma'am, we
Yes.
should take A transpose now for finding row space.
Uh, no. Even you can go with
No,
you can convert this to the row echelon form, a row reduced echelon form, and you can take the non-zero rows of U, and that will also give you the row space of A.
That's why I think.
Why is the answer not coming? Yeah. Is this calculation right? I don't think I've done the mistake. 0 5.
After reduction, the second row is 0 minus 2, 6 minus 2. Right?
After reduction, second row is
0 minus 2, 6 minus 2. Right?
yes, but again you can divide it by minus 2 and it becomes this.
Thanks, Arvind. I think it's a good statement.
Ma'am, I think we got to check the row too.
My row 2 is wrong.
Yeah,
24681305 163.
the minus 2.
Yes, I want you guys to
Minus 1,
solve the
3,
problem,
minus
but
1.
don't solve the.
Yeah, it's definitely got to check it again. Can you put the couple of steps there before we go to the final result what you have given?
Okay, so R2 is replaced by R2 minus 2 R1, so it is 0. 4
Yeah,
minus 6, which is minus 2.
minus 2. Yes.
6, this is 6, and 8 minus 10, which is minus 2.
Mhm.
Ma'am,
3 minus, yes.
ma'am, actually, a simpler way, like you could add the first and third rows and then subtract with the second row. So R1, R2 such that R2 minus R1 plus R3. So 1 plus 1 is 2, you subtract with 2, and 3 plus 1 is 4, subtract with 4. It gives
Oh, these
it's
two are the sum of,
yeah, yeah, yes, ma'am. So you could actually do it in one step. You'll get the zeroth row.
yeah.
No, but you can complete the way what you're going, then you try for the alternate.
So this becomes, okay. But still, the answer is not coming right. Sure. Or maybe the
Maybe it is some other
option, yeah,
basis.
some other, yeah, maybe it's some other basis, yeah.
Row 2 and row 3
Maybe we are
is
able
same.
to,
And we should
no.
check whether those rows are no
Okay.
multiples of row 1, row 2. This.
Yeah, so we got 1305 and 013 minus 31, right? This is 000. Okay. What is the answer given? It should be some other basis, definitely. I think that is why
Ma'am, row 2 and row 3 are same, no?
92. Yeah, row 3 and row 2 are same. 1092. 1092 it is. 1092. I think it's okay. Even this would be an answer for this span of these two rows, right? And this would be answer. I, because they are definitely linearly independent, these two rows, and we can write span of these two rows as the row space of A. It is okay, I think. There is no
This
error over here.
1 times 1 vector 1092 plus 3 times the vector 01 minus 3 1 gives row 1, ma'am. So they are multiples.
10.
No, one times vector 1092
Okay,
plus 3 times vector 01 minus 3 1 gives row 1.
three times it is. Um, no, it's okay. Yes, yes, it's giving. It's giving. Yeah.
So that shows this whatever basis we found is a linear combination of this basis.
Yeah. What we found is this one, right? 1305 and yeah, and this we are able to write as a linear combination of these two vectors.
left hand
So
side,
both the
right?
methods
And
don't have the same spanning
as
set.
part of that, we have
Um,
brought our
yeah, can you repeat again?
started
So
applying
both the
it to
methods
our
don't
element
give
as
the
well.
same
But having said that,
results.
we
Like
did
the spanning set
we
is
have
different. Right?
No, I'm not
do a
able
lot
to hear. Can you write? Can you write over here? Both the methods do not give the same spanning set. Yeah, it's not giving the same spanning set. Yeah, but the base is also not unique, so I think it should be all right.
Whatever I've written, is it correct? When if we
Yeah,
change the method, the basis also changes.
yeah, and we know that the bases are not unique, right? So this is not something which is unique. So you can have different bases. That is okay. S- so have you noted down the textbooks that
The
I?
second vector is same as the second vector.
Yeah, the second vector is coming out to be same.
Yes, and one is
Yeah,
a linear combination.
one is a linear combination of the other two. So did you note down the textbooks that I had written? Yes, okay. Also, next week we are not next the quiz week we are planning to have one session with Sir. So Professor Prashant may take one session during the quiz week. So we'll keep you informed about the schedule.
So, ma'am, would you mind in really deciding the schedules not clashing with the already planned schedules? Just today's
Uh,
schedule is clashing with the previous.
it is not possible to like keep it complete like you'll like the schedule that we have currently is I don't think it clashes with any regular session.
It is clashing with the regular session. Today's current session is
No, no,
clashing.
today's will be clashing because we had kept it separately, but in general it won't. Yeah.
2 days in a week it is clashing, and yeah, it's not may not be possible to really cover the entire week without clashing. One or two classes, okay. But unfortunately, if you are really clashing, then record that one. It will be helpful. So you are not recording and you are letting the two clash with others. At that time, unfortunately, all the other classes also not recorded.
Yeah, yeah.
So I think someone has to do the study. I mean, if you really record it, then there is absolutely no one cares about it, even if it clashes. People can take time to really go through that one.
Yeah.
And somebody is really making a trivial calculations and saving something, not by not recording.
Yeah, we'll take care of it. Yeah.
Yeah, just invariably just record it. What is going? What did it cost anything?
No, no, like we can record the session. So
Yeah. In fact, many of the sessions, even if you are a silent observer, you continue to learn because others' doubts are really a good prompts.
yeah, understood. Yeah,
Yeah, thank you.
yeah. Thank you.
Ma'am,
Yeah, Prashant.
ma'am,
Uh,
the basis for the row space is different when we take the row echelon form, A transpose.
basis of the row space is different when we take the
A transpose method.
A trans. Then you are getting a different basis.
Yes, ma'am. Also,
Uh,
there will be two different bases, ma'am. One when after we take the row echelon form in the row echelon matrix itself, and one more in the A matrix.
okay. Yeah, it is possible. Like it is possible to get different bases for different methods. But at the end, like rank and nullity, all that will be uh, like just a number, right? So it is okay. Also, last class you had asked if we have two vectors, sorry, two planes orthogonal, then should all the vectors lie on the same plane? Something like this.
Shrikant sir actually told that if a vector lies on the plane, it should fully lie on the plane. It
Yeah, it should fully lie
should not
on the
just
plane.
touch the
Yeah,
plane.
yeah. It should fully lie on the plane. Yeah,
So I think orthogonality is.
yeah, yeah. That is what I just wanted to clear.
So if two planes are orthogonal, then the vectors in each plane will be 90-degree to each other.
90 degrees to each other. Like
Okay.
the whole vector should lie. Like you can think of it as uh, so if you have any plane, the whole vector should be on the plane. It's not that just one position should be on the plane. The whole vector should be on the plane, and even the on the other plane, which is orthogonal, even there the whole vector should be on the plane. Then only we say the two planes are orthogonal.
When two planes are orthogonal, then the two planes they will cut each other at 90-degree. So the planes will be perpendicular to each other.
Yes.
Okay.
Yeah.
So graphically, if we see, so the
Graphically, you can think of maybe the two walls.
two, okay, like
Two
two,
wall. Yeah.
okay, yes. So they will intersect at 90 degrees, the two planes.
Yeah.
Okay.
Okay, then we'll close the session now.
Ma'am, if row
Yeah.
space is independent,
Rather,
column space is independent, ma'am, because like when we said about invertible matrix,
When we say about invertible matrix, yeah.
the columns are all independent and the rows are also independent.
Right.
So I think that is why when row space is independent, column space also should be independent for a square matrix.
Uh, no, what do you mean by row space and column
No,
space?
rows are independent. All the if all the rows are
Yeah, yeah,
independent, then
rows. Yeah,
it
yeah.
implies that all the columns are independent.
Yes, yes, that will imply. Yeah.
So I think that is because we when we said that the matrix is